We will start with digital circuits. Digital circuits are very typically operating with zeros and ones. There are some special values like state of high impedancy, which is typically used for the communication on buses. But in this case, we can say that digital circuits are operating with two logical values, which is logical 0 and logical 1. These values are used with logical operations. You know them from the languages like C or C++. It's typically AND, OR, and exclusive OR, and etc. There are two examples for the AND and OR. You can see the schematic symbol and the truth table where we have inputs and outputs. A and B are inputs, and the last column is the generated output. So we have all combinations of inputs and which produces some output. And the third, or there is also the equivalent in a C language. So logical operations are then grouped into logical equations, where we can use Boole's algebra to simplify them. And if we want to express the logical equations, then we can use the let's say digital circuit. We can use the equation, or we can use the truth table. I will demonstrate it on a simple 1-bit adder. The 1-bit adder is typically consists of two half adders, where the half adder has two inputs, A and B, and this half adder generates the carry for the next stage, which is the output C and the value of the sum. If we write down the truth table, and if we fill the outputs, then we can infer the equations that the sum is equal to the A XOR B, and the carry to the next stage is equal to A and B. This is the half adder. The full adder has let's say another input, which is the carry from the previous stage. And on this slide, you can see the implementation using the digital circuit. Using the digital circuit, we can identify the half adders. Do you see my mouse?
Yes, we see.
Yeah. Excellent. So this XOR gate and this AND gate is the first half adder, and this XOR gate and this AND gate is the second half adder, and outputs from the carry generations are ORed together to generate the final output. So this is a simple 1-bit adder, and if you connect these adders in the chain, then you can get the n-bit adder. Again, we can also write down the truth table, where we enumerate all the inputs, and we will write down all the outputs. This truth table can be encoded into the special memory, which has a 3-bit address and 2-bit output, where we encode the value of the sum and the value of the carry. And this is crucial for FPGA because FPGA very typically encodes this logical circuit into the truth table, and after that it generates the content of the memory, which is addressed by the inputs. You will see it later. So this is another possible implementation of this. If you have a 3-bit memory with 2-bit output. Digital circuits are typically divided into two main groups. The first one is the group of asynchronous circuits, where the output or outputs directly depend on inputs. The example can be the 1-bit adder. As you can see in this example, we don't have any clock signal. The synchronous circuit is can be understood as a sequential logic. So this kind of digital circuit is clocked by a clock signal, and the output depends on inputs and history. So very typically you have a memory element inside this circuit. For example, the 1-bit register, which is called as a D flip-flop. And for example, the register is a circuit where the input, when the input is passed to the output and hold and hold after the rising edge of the clock cycle. I will show you the example on the next slide. Another example of synchronous circuit is the finite state machines, or is the implementation of finite state machine, which can be, for example, some control it can be, for example, the controller of a digital circuit which controls how we are communicating with another components of the digital design. The synchronous and asynchronous system circuits together is, for example, the ARM processor or another different digital circuit. And we are typically using together the synchronous and asynchronous circuits to implement the hardware accelerator. I was already talking about the timing. As I already said, it's another dimension which we need to meet, or which we need to meet during the development of a digital design, and typically we need to hold two parameters, which is the setup setup timing and the hold timing. As you can see on the diagram, there is a clock cycle, and on the rising edge we need to before the rising edge we need to have the input data valid. And we also need to have the data valid after the rising edge. This is because let's say it's a physical constraint of digital circuits, because if you don't meet this timing, then you will fall into the metastability issue, which isn't good, because during the metastability you are not able to decide if the output of this block is 0 or 1. So this is the physical requirement of the technology. Now, how the FPGA looks like? It's a 2D structure of configurable logical blocks, which are connected together via a configurable interconnection network. Then we also have some special blocks which are dealing with the output and input from the FPGA. So using these outputs, you are able to communicate with another circuits on the board, and very typically the FPGA also contains some special blocks which are hard coded. For example, the FPGA has some blocks for communication on a high speed with external devices. It has embedded memories, digital signal processors, CPU cores, and so on. Now, if you look into the CLB, we can see that there are two slices for the case of the Xynix FPGAs. The structure of the configurable logical block depends on the FPGA vendor, but we can say that the structure is more or less the same. They are just different names. Inside the slice, we have a lookup table, which is a 4-port memory. So you are able to implement a logic function with 4 inputs and 1 output. There is also there is the 1-bit register for the implementation of synchronous circuit. As you can see, it's clocked by the clock signal. And there is a multiplexer which allows you to select between the, let's say, live value from the lookup table. This path is for the implementation of the asynchronous digital circuits, and this path is used for the implementation of synchronous digital circuits. But this is very simplified structure of the slice. If you are interested, I can open you the documentation for one FPGA, and you can see the whole implementation of the slice. But I think that you don't need to see it. But the slice architecture also contains some special connections to another slices to implement a fast carry logic for the fast data transfer to the next slice and so on. FPGA also contains RAM blocks, which are typically distributed in columns, as you can see here in the figure. I've also looked into the documentation to demonstrate that the memory on the FPGA is not so big. As you can see, for the case of the Vertex 7 FPGA, we are able to use, for example, the 6 megabytes of memory, and for the Vertex UltraScale FPGA, we are able to use approximately 16 megabytes of memory. So as you can see, internal memory is not large, and the external memory is really needed. Due to this, the FPGAs are also, some FPGAs are equipped with the new generation of parallel memory, which is the HBM or HMC.
Sorry, but if everyone can mute because there is some noise background. Thank you very much.
Okay, thank you, Xavier. Or there is also possibility to connect the external memory to the FPGA. In this case, the memory controller can be implemented in a logic, or there can be a special hard-coded block. It depends on the FPGA. The FPGA is also very typically equipped with digital signal processor and special multipliers blocks for the implementation of more complex multiplication computation, for the implementation of more complex computation of equations where we need to multiply values together, and they are again distributed in columns across the FPGA. The clock signal is distributed in FPGA using the clock tree, which is a special low latency network for distribution of clock signal. And as you can see, it's the structure of the clock tree is like this. There is a clock signal connected approximately in the middle of the FPGA, and then it's distributed in this regular shape because we want to have the, let's say, latency of the clock signal is required to be as minimal as possible. The FPGA also contains the clock manager, which is a special block for modification of source clock signal, because very typically you have a source of the clock signal on the board. Let's say that the generator generates a signal on the frequency of 100 megahertz, but you want to run you want to run your design on the half frequency. So you need a special block which is able to modify the clock signal, and this modified clock signal is then connected into the clock tree to provide a reference clock for the design. This block is called as a clock manager, or a DCM, digital clock management. This circuit is capable to modify the frequency and the phase of the clock signal. As you can see, there are output named CLK. So, for example, from this output, the clock signal is shifted by 90 degrees, and so you have a lot of capabilities how to connect your design on a desired clock. The FPGA also contains some digital designs can be, or some cores can be implemented as a soft core and a hard core. The soft core is implemented in logic, so it's implemented in these configurable logical blocks, and this means that these blocks consumes resources on FPGA. So they are synthesized during the code translation, and very typically these kind of blocks runs on a low frequency and they consumes more resources based on the complexity of the implemented core. But some cores can be are named hard cores, means that they can be directly used from the digital design, but you don't need to synthesize it because they are implemented on a FPGA, and if there is some mistake, then you are forced to live with it because you cannot reprogram these kind of blocks. The example of these blocks can be, for example, the PowerPC core, ARM core, or CRC32 blocks.